Okay, welcome everyone to this video for section 4.5. It's the last section in our section on integrals. And it's also the last video of this lightboard series. Okay, so really well done for getting this far, and this is just going to be a short video where we're going to introduce quite an interesting result. Okay, so this is on Green's theorem in the plane. Okay, named after me. Nope, just joking. It's named after British mathematical physicist George Green, who lived in the 1800s or so. And in 1828, he published an essay on mathematical analysis for electricity and magnetism. And in it, he had a result similar to what we're going to look at now. And it connects a line integral. So here's a line integral of the second kind, a dot dr, okay, around a closed curve. So if it's a closed curve, we put this little circle on the integral sign to denote that it's closed. Means integral around the closed curve. Okay, here we're going to think about this vector A as being something with x component p and a second component q, where p and q are functions of two variables. Okay, so our line integral a dot dr can be the integral of p, so it's a dot dr, so it's p dx plus q dy. And again, we're going around a closed curve. Okay, so p and q are functions of two variables. So p is p of x and y, and q depends on x and y too. All right, and the statement is, the theorem is, that this line integral equals a double integral around the region S that's enclosed by this curve of dq by dx minus dp by dy dx dy. Okay, let us draw the region. Okay, so we've got some region S. Okay, and it's understood that we take the line integral in the anti-clockwise direction. So we go around anti-clockwise. Okay, so this is one smooth boundary. Okay, so the double integral involves this region S. Okay, and the line integral takes us around the boundary of this region. Okay, and it's useful because if the double integral is too hard to do, we can resort to the line integral. Or if the line integral is difficult, we can resort to doing the double integral. Okay, so you can ask yourself, what's the area of this region? Okay, and rather than doing the double integral, we'll see that there's a certain p and q that just, so that this term drops out and this just becomes the area, and we do a line integral. Okay, so you can find the area if you just traverse the boundary, keeping the region on your left. So let's try and prove this. Okay, let's think about the right hand side. And let's just think about the dp by dy term first. So just think about p first, and then we'll get a result that equally applies to q. But let's think about a different region than this one. Let's think about a region that takes some values of y here, that goes between x equals a and x equals b. So this is the x-axis, this is the y-axis. Then we go vertically up, and then some different curve back to x equals a, and then we go down this way. Okay, so this is our region S. And the line integral, this line integral corresponds to going around this in an anti-clockwise fashion, so that the region is always on your left. Right, so let's think about this term that I've highlighted. It's minus the integral of dp by dy dx dy over this region S. Okay, now we know how to do these double integrals. We can write this as an iterated integral where we go, let's do the integral over x last, and let's do the integral over y first. So let's do dp by dy. We're going to integrate over y first. And again, the key point here is thinking about our limits. All right, so we're going to do this double integral by thinking about the strips. So we're going to do the integral over y first, so we're going to think about these vertical strips. Okay, so what are our limits on y? So at any value of x, we're going to go from y1 of x. Okay, we don't know what this curve is, but let's just call it y1 to y2 of x. y1 of x to y2 of x. And we go from x equals a to x equals b. All right, now the integral of dp by dy is just p. So this is just the integral of dx p evaluated at y1 of x and y2 of x between a and b. Okay, so let me write it here. It's minus the integral between a and b dx of p of x y2 of x minus p of x y1 of x. Bracket there, and let's have a big brace here. Okay. Okay, between a and b. Now we can write this as, so we swap the minus signs. This goes from a to b, this term first, p of x y1 of x dx. Okay, and now we have a minus sign, p of x y2 dx. Okay, between a and b. So we're going from a to b along this part. Okay, we go up here, which doesn't, so going up the line integral here doesn't change x. Okay, so this part and this part don't contribute if we think about the line integral. And then we're going from a to b along this y2. Okay, but we don't want to do that because we want to go in an anti-clockwise fashion. So we want to go from here round to b, vertically up, and then we want to go from b to a. So let's swap these limits. B to a, and if we do that we need to change the sign, so we get a plus. Okay, this plus this takes us from point A at y1 along this bottom part. It takes us vertically upwards. Okay, and it takes us along this top part, y2, and vertically downwards. Okay, this plus the vertically up plus the vertically down, which are both 0, equals the line integral of p x y dx. Okay, around the closed curve from here to here to here, back to where we started. Okay, so we have proven it for this term with this term. And if you just think about Q in the same way, then you just get the same thing, okay? Except you'll think about the line integral in the y axis. Okay, so this is a really useful result. And let's now think about how we can use it to calculate an area. Okay, so let me clean the board. And again, this is all in your notes again, so if you want some more details, maybe you'll find them there. So let me clean the board and we'll look at area. Alright, so how do we calculate the area of some randomly shaped region? Okay, so what's the area? The area would be the double integral of just dx, dy around that region S. Okay, this is the area. Alright, so can we arrange it such that this bracket will just be 1? So we want dq by dx minus dp by dy. We want this equal to 1. Okay, how about we have q equals x over 2 and p equals minus y over 2. This means that dq by dx will be 1/2 and dp by dy will be minus 1/2. Sorry, 1/2 is dq by dx. dq by dx equals 1/2 and dp by dy equals minus 1/2. So dq by dx, 1/2 minus 1/2 will give us 1. Okay, so we have that the area of a region dx dy, the area of the region S, can be given by the line integral. So if you want to find this area, you can do the following line integral. You go around the curve, the boundary of the region S, keeping S on your left, so you traverse it anti-clockwise. And now we've got p dx, and we said p was minus y over 2. So minus y dx, and let's put a half out the front. Okay, and plus q dy, plus q is x over 2, we've got the half already, dy. Okay, so this is a line integral that tells us the area of a region S. Okay. So if you want to know the area of some large field, you can just walk around the boundary of it and calculate this line integral rather than do the double integral. Okay, it's quite an interesting result. Okay, so there's some intimate relationship between the area of a region and its boundary. Alright, so let's look at one example and then that's us done. Alright, so let's think about how we calculate the area of an ellipse. Okay, so here's an ellipse with axes A and B. Okay, we looked at this in section 1. Okay, and before, just a second ago, we saw that the area could be written as 1/2 the line integral of minus y dx plus x dy. So this is the area of our ellipse. And again, this integral with the little circle means it's a line integral around a closed loop taken in an anti-clockwise direction. Okay, so how do we parameterize our ellipse? We have that x equals a cosine t and that y equals b sine t. Okay, where t goes from 0 to 2 pi. Alright, so we can write this line integral, 1/2 around the closed curve, minus y, so this is minus b sine t, dx, so if x is a cosine t, then dx is minus a sine t, minus a sine t dt. Okay, and so that's the first term done. Plus x dy. So x is a cosine t, and dy will be b cosine t dt. B cosine t dt. Okay, so we've rewritten our line integral just in terms of t. And changing t from 0 to 2 pi will take us right around the boundary of the ellipse. Okay, so this goes from 0 to 2 pi. We've got a 1/2 out the front of a b sine squared t dt plus AB cosine squared t dt. Okay, so we've got a common factor of AB over 2, integral between 0 and 2 pi of sine squared plus cosine squared, sine squared t plus cosine squared t dt. Okay, and of course this is just 1. So this just leaves us with AB over 2, integral between 0 and 2 pi dt. Okay, and this just equals 2 pi times AB over 2, which is pi times A times B. Okay, so this is the area of an ellipse with axes A and B. Okay, so this is minus B and this is minus A. So the area of an ellipse is pi times A times B, and we got that from doing a line integral walking along the boundary of the ellipse in an anti-clockwise fashion. Okay, so this is a very powerful result. So here we did the line integral to get the area. Okay, sometimes it's useful to do the double integral to get the line integral. Okay, just whatever makes it easier. Alright, so that is the last of the videos for section 4, and it's the last lightboard video actually. So I hope you've enjoyed them. I hope that they've improved your understanding or helped improve your understanding of the material, and that they'll be useful when you come to do your revision and right through your degree pathway. Okay, like I said, this mathematical apparatus that we're learning about and developing, it's used in lots of modules in your course right across mathematics, physics, engineering, etc. Okay, it's calculus in 3 dimensions. We live in a 3-dimensional world. It's what we need to describe things. Okay, so with that, just enjoy section 5 and 6, and I look forward to seeing you in the future.